Um, yeah, we have a lot of sharings, we have a lot of webinars. So perhaps it's till the end of the week. Not very many people are joining us. It's okay. It's okay because we will post this video afterwards on YouTube. So it's okay. I'm totally fine if we don't have a lot of people. And typically we know in China, we count like Sunday as the end of a week. So we typically recognize Monday as the starting day of a week. And sometimes in Western, for example, in United States, we call Sunday to be the start of a week, which is sort of contradicting this idea of weekend, right? We have weekend, that's the weekend. So I would prefer Saturday and Sunday towards the last 2 days of the week. All right, so we're getting towards a fresh start tomorrow, March the 1st. All right, so the reason I want to talk about 10A at the very beginning, oh, my bad, I should switch it to B. Is that we have 10B right after that, and I heard from my students that they can get better once they have joined the sharing for 10A, which is a very, very good thing. And technically, starting from AMC 10, 12 towards AIME, there is a big change. So right as a moment, and we have our Chinese New Year, we have a lot of things. And very tough preparation for my courses. So we have this sort of delayed towards this time. But it's okay. So still we want to have a brief discussion what happens for this AMC10B. And I believe if you still are interested in this, perhaps you want to get some info, get some knowledge about AIME, like some preparation or some basic info. So we'll have a brief discussion. And if you have any questions, raise it up, let me know. And if I can answer it right as a moment, like it's not too hard for me and my answer wouldn't be too long, perhaps I'll talk about it. And if it's too long or too complicated for me to answer at this moment, maybe we'll save it for the future. How does it sound? Well, that's what we did in 10A, but since you can see a lot of analysis for 10B, so we can go over that sort of faster. All right. For example, the first one, last time I was suggested to mark these answers at the very beginning. Let me see, please. Please keep muted once you join it. Thank you. The first one. The first one is B, or 19. So I started another page so that I can look for all my work there. I collected and worked on most of them, and some I checked with my colleagues, checked with other teachers, because we have some similarities in between these questions and previous questions. So it looks like a very good chance so that we can talk about some of these. The first one is x less than 3 pi and greater than -3 pi. So in fact, a very quick start is that we know it should be odd, right? Because we consider 0. And if we have, say, n there on the positive side, then definitely we want a -n. So immediately we can cancel B, C, and E. So this is a quick observation. Later we can count how many terms are there. Right, so if you only consider 0 to 3 pi, you will have something like A, but this is not true. And that is all for problem 1. Now let's see problem 2. I heard some of the students got it wrong, and that's the reason I want to talk about algebra all the time. Algebra, algebra, algebra. Be careful to that. Take the longest time. Spend as much time as you can on algebra, because as far as I know, for students in the United States, to be honest, especially in school, students really lack of this training. For example, in my class, when we work on all this, say, sequences, when we do some simplification with respect to factorization, I notice a lot of students couldn't do it in a nice and simple way, and to have a short time and also correctness. It's super hard. However, if we do have a lot of training, that shouldn't be a problem. Let me see what is the answer for problem 2. Okay, so it is well, the only thing that we need to take care of is the first one, because the second one we know definitely is 3 plus 2 root of 3. That is for sure. And the first one, what is that? This is the absolute value by definition. Once we take the square root, we have the absolute value for that in the inside thing. And we need to compare these two, which one is larger, which one is smaller, to be honest. And this one is actually 2 root of 3 minus 3. To compare that a few ways, for example, if you memorize root of 3, this is something around 1.723 or something 1.72 at least. I know that is the approximation. And if you couldn't compare that directly, you can think of like 3 is the square root of 9 and 2 root of 3 is square root of 12. Of course, you can compare those two in this sense. And then once we have 3 and 3 cancel, then we know the answer should be 4 root of 3. So this kind of things, this kind of mistakes, we shouldn't have in the future, especially if you're moving towards AIME. This shouldn't be something you're worrying about. I have some students like, hey, I can get 120 or maybe at least 110. Probably I can get into AIME. And when we try to work on some AIME problems, it looks like still it's quite hard to solve them in a short time. One of the reasons is that very hard for us to find a correct answer. And also, we want to like check it all the time. So I know a lot of students are trying to say, can we check it? Can we save time checking? A lot of time is spent here. And let me see, number 3. The answer is C. So actually, we're talking about this, say, system of equations. For example, if we count junior students as X and then seniors as Y, right? Junior as X and senior as Y, that is what I said. And then we have, for example, X plus Y equal to 28. And there we have 25% of X is equal to 10% of Y. So we're looking for all these debate team because we have equal number. So that comes from the equality, and then we have 25% and 10%. Also, another one is 28. So this one is more like AMC. We are trying to look for all this information in between. What kind of information, what kind of equations can we set? In fact, we only need 2 of the informations, and then we have 2 equations. You can solve to get X. That is enough. Problem 4. Problem 4, let me see, what is the answer? B. Well, this one is sort of tricky, but still, since it is the first 10, we shouldn't spend too much time on it. Why? Because we have, say, these blue and yellow shirts. So we have blue pair, we have blue yellow pair, and then we have yellow pair. And then we notice that for blue pair, it counts for 2, and for yellow pair, it counts for 2 as well. So actually, we're dealing with this double counts, right? So we have 66 pairs in total, and exactly 23 are wearing blue shirts. So we have 23 pairs, number of pairs, and number of students, or number of shirts, and our number of students. Then we know there are 46 of such. And then together we can count how many count for blue and how many count for yellow, and there we can find this pair. So there we have 32, and in fact, the difference will be 46, 57. We should have 11 of such students there, and then if we have 11 blue, then we have 11 yellow to have this blue-yellow pair. There we go. And in total, we have the total number of yellow shirt students, or yellow students. That's all for problem 4. And what about problem 5? Problem 5 is B, I hope. Distinct single-digit positive integers, 2 of those together to get 24, and the other multiplied to get 30. Well, that sounds really like AMC8 problem, isn't it? Quite similar to AMC8. Something like that. So one of them is 30. So 30 is equal to 5 times 6, and there's no other way that we can split it into 2 single-digit positive integers. So that's all. And what about 24? 24 you can split it in terms of 3 times 8 or 4 times 6. However, 6 is occupied, so we couldn't take 4 times 6. That's the only issue we have. So then we have 3, 8, 5, 6, and what is the sum? Just sum over all of these. 3 plus 8 and 5 plus 6. So perhaps the only one that might be confusing is that 5 plus 6 plus 4 plus 6, which is 1 less, right? So 21 is the only confusing term. If we can factorize 30 and 24, there's no other possibilities for C, D, and E. And problem 6. Yes, I'll try to remind myself every time, show up the answer first. This is C. 76. So mean of the scores in the morning class is 84. And mean in the afternoon class is 70. So morning we have 84, and afternoon we have 70. So those are the means. Moreover, the students in the morning is ratio is 3 to 4. So it's like 3 to 4 in terms of students. Of all students. Well, this one is more like the mixture of something like a blend of Jews or weighted sum, right? This one also is something we typically talk about in AMC8. It is more like a weighted mean, weighted sum. So we can have like 84 times 3 over 7 plus 70 times 4 over 7. However, I introduced that a lot when we try to deal with this kind of weighted sum. We can just take a benchmark so that we don't need to worry about all these ugly numbers. I wouldn't use the word ugly numbers because that really take time. For example, if we use, say, 70, if I'm a bad guesser, I can just take out the benchmark as the lower part, and then I'll have 14 times 3 over 7. Right, so then we have 6, and this is 76. Or if you feel like I can make some better guesses, then definitely we can guess something around 76, 77. For example, if we use 77 as the benchmark, then we will have like 7 times 3 over 7. And the other part will be minus 7 times 4 over 7. You will see that immediately we have a minus 1 there, right? Together we have plus 3 minus 4. That means we can think of a minus 1 change out from 77 instead of doing the products, doing the first 2 products. Again, this will provide us 76. And problem number 7. Problem number 7, what's my answer there? D. 65 pi. So we have these 4 circles, and then we are having those tangent to the line at the same point. So that means they're on either side. Let's make up this line, and then we are having circles, circle on top, circle on bottom, small circles there, something like that. We have 1, 3, 5, 7, and consists all the points that lie inside exactly one of the 4 circles. What does it mean? That means if I have a smaller circle, then I no longer consider what is inside. Of course, this one is just a legend. It is not precise because they are tangent to the same point. But that means we only consider the difference here. And hence we are considering all these contributions, like how we can have it as much as possible. For example, if we have that 1 to be covered, maybe 1 and 3, right? If I have that, then that doesn't change anything. If I have that 1 on the bottom, I'll take 1 more, right? I'll take some more. So we're expecting that 1 and 3 are covered together. This is a quick observation. Quick up that we want that like 1 and 3 to be overlapped. Something like that. And then we can think of like 3, 5, 7. Of course, we know 7 should be somewhere there and 5 should be on the other side. 7 and 5 to be opposite, to contribute as much as possible. And what else? There's no difference because 3 should be somewhere. 3 should be covered somewhere and 1 should be covered somewhere. So that is enough, right? So we have pi times, they're already, that's fine. 7 squared plus 5 squared minus 3 squared, that's all we have, in fact. So this is how we analyze this kind of problem. Nice and simple in the first few problems. And problem 8. Problem 8, let me see what is the answer. 8. Well, to be honest, when I first see it, I did it wrong. So I double check it because I have to compose my solution. So my suggestion for students is that if you're trying to work on those questions, not only have a draft, but better have your draft ready to be read, like it's organized, so then you can check it immediately. Typically, if you write a few sentences, if you write a few equations, you will notice that does it really make sense, right? A quick browse will tell you that something might be wrong. And especially for this detailed calculation, there's no control. So we need to trace it back to our daily training, daily practice, such that once I do addition, subtraction, multiplication, division, or some powers and distributions, I wouldn't care about the signs or like I missed one of the distributors or something. That shouldn't be happening here. Or that's something we should take care of at elementary school or junior high at very early time. All right, so second row. What is the second row from the top? So if we have, say, something like 1 to 225, we know it is rotating in this way. And then, what are the observations? It looks like we're having all these out powers. Let me change another color. We have all these out powers along these diagonal. This is something we can control. And then the other, well, sort of like diagonal is that we have 4, 16, and then keep going. We have all these, but that doesn't help much. So in this sense, we may refer to all these diagonal terms to help us figure out what is the second row, right? Because we know the second row should be something, we don't know, in some order. If we have 225, then eventually we're having the last row, the top row, to be something like this, right? In this direction. We have 225 there.
Hello.
Hello. And then that means this is the upper right corner, but that is the top row. And since we notice that this is the pattern, like the consecutive odd squares, then the previous one will be 13 squared, right? That is 15 squared. So we will have 169 there, and then we will have 170 to its right. And moreover, we are having something there, and since we have this direction, Right, so the greatest number and the least number. So now we need to figure out what is the largest, what is the smallest. Since we have this one in the structure, this one is the smallest. And its neighbor is the largest because that one will be the latest one showing up. And then we can determine which one is which. Because now it's 15 by 15, so then we can tell the largest and the smallest. All right, so let me see. For this one, we are having it in terms of 221 because the top row will contain 15 of that. So we will have these numbers, this largest, to be 210. Wait, not 221, 211, my bad. Going this way. That's better. So we have 211. Yeah, from 211 to 225, we have 15. So then we have 210 to be the largest. And then what is the smallest? Then we will consider moving from 170 or 169 towards that. So this one can be found to be 157. Well, this is a little tricky. Although it's problem 8, it takes a little bit time to figure out the number. Well, at least so far, I didn't find any better ways to be more precise and also save time. But if you have any, you're welcome to tell me. All right. As I always tell my students and those parents, teachers are not superheroes. As Socrates said, like if you know more, then you will see that there are there's more thing that you don't know. So typically, telling us that we don't know something, it's okay. It's okay. Problem number 9. The answer is D. 7. Well, this one, I did it brute forcefully. So the idea is that we are trying to recover it. Of course, there might be some other ways. So this one, I would say that this refers to analytic geometry. Because we want to figure out this symmetry after some sort of translation, after some reflection. What do we have, right? We have all these transformations, and typically the main 3 transformations are translation. It's like a shift. It's not translation word to word between languages. And also we have reflection, and also we have rotation. Now, those are some basic transformations. And also we have some other things. For example, in linear algebra in college, we may consider something like contraction, so or dilation, like if we extract that or if we compress it. But after all, they're working on this idea, like how can we find this change? How can we find the resulting point one by one? So say, for example, if we consider the first one and then reflect it about y equal to minus x. Say I have this transition from P to P1 to P2, and then we know P2. P2 is minus 6, 3, and then we can do it backwards, right? So this is this kind of analysis. This one is again by symmetry with respect to y equal to minus x, because reflected about this line is the same thing as moving back or looking at the mirror. And for that, we switch it, and we switch it to minus 3, 6. And then rotate it with respect to 1, 5, then we can generate our coordinate system. Minus 3, 6 is somewhere like here, and then we have 1, 5, somewhere here. So then we will rotate it back to some point like that. Something like that. What is the final answer? This point P is, I believe, 2, 9. I'll save time for the calculation. But anyway, this is the way we do it. Like originally we do it counterclockwise, then this time will be clockwise. 90 degrees. And the result will be 2, 9, and the difference will be 7, naturally. What about number 10? Well, number 10 is brute force, and this one is quite similar to something we have in AMC10A, right? This year, is it problem 11, problem 12? We have that with respect to cone. So it looks like this year we do have something with respect to cone calculation. Cone calculation. Is that 11? Is it problem 12? Yeah, I'll give that a quick check. Later, I'll tell you what is that. Let me load the page. And then for this kind of analysis, which is finite, right? What is the height for that? Inverted cone is full of water. So the volume, the base radius, this one will be 12 squared times pi times height, 18 times 1/3. This is a volume for water and poured into a tall cylinder whose horizontal base has a radius 24 centimeters. And then what is a height for that? Well, we need to assume that it is full, isn't it? The cylinder. And then we have like pi times 24 squared. So we have this cone originally, and then we switch it to a cylinder. And we're looking for this height. And that will give us the height. So it's just like pure calculation. Sorry, I forgot to mention the answer at the very beginning. The answer is A, 1.5. So this is problem number 10. Next, problem 11. Ooh, there's no number. Just finished baking a large rectangular pan of brownies. So at first I feel like this one is really weird. But after reading all this, I noticed actually we can solve for that. So equal size and shape and straight cuts parallel to the side. So that means we're having like small squares or small rectangles. We don't really care. Rectangular pieces, of course, rectangles. Must be made entirely across the pen. That means we are not having something like L-shaped stuff cut through. So if you have a line very parallel, then exactly we're splitting those across the cut into two parts. Same number of interior pieces as pieces along the perimeter of the pen. So it looks like we're trying to figure out some sort of number such that we have this characterization. For example, if we can call one of them to be X, one of them to be Y, of course you can say length and width, up to your preference, it's okay. What does it really mean? That means if we're looking for this outside and the interior, we know they're of the same area. And can we make it better for this characterization? Of course, yes. How? That is my question. How? How could we have that to be better? Because we want to show, we want to represent this circumference. That is the difference. How about we consider the whole area? Right, that one will be 2 times the interior, which makes it even simpler. And the interior is exactly X minus 2, right? So we're taking 2 units out, and then we're taking 2 units out there. So it is 2 times X minus 2 times Y minus 2. Now it becomes algebra and number theory. So we can just simplify it. There we have 2xy, xy equal to that, and the minus like this is minus 2 minus 4x minus 4y plus 4 plus 8 together. And there we have xy minus 4x minus 4y. And at this moment, if you have seen this trick before, then we know we are trying to complete this whole thing, which is x minus 4 times y minus 4, something like that. So we're expecting a 16. And then to complete that, we are having 8 to the other side. So 8 is here. What is the greatest possible number of brownies she can produce? What does that mean? Our goal, the problem, is to maximize our x times y. And here we have a few solutions. For example, we can have, say, x minus 4 equal to 8, y minus 4 equal to 1, but then maybe they're not too large, and then we have x minus 4 equal to 4 and y minus 4 equal to 2. And in fact, if we consider the symmetry, then we don't need to consider other solutions because they no longer contribute. So here we have x equal to 12, y equal to 5. Wait, is that? Oh, okay, so that's the, and then we have x equal to 8 and y equal to 6. See, along our analysis, sometimes people make mistakes, but it's okay if we can see what is going on there, right? And afterwards, we can see things are getting harder and harder. What is the ratio of the sum of the odd divisors of n to the sum of even divisors of n? So this one, at the very beginning, it looks a little bit weird. Because we want to know what is the sum of odd divisors. Let me see what is for 10a, the cone one. Yes, it's problem 12. Yeah, the answer is problem 12. I have found it. There, problem 12. The ratio. So first we want to find the sum of odd divisors for that. And later we want to find the sum of even divisors of n. Well, we know the sum of all. Or maybe we can call this to be large O and this one to be large E. Together, if we have a whole sum, right, O plus E, this is something we can find directly. Originally, we have n. N is equal to 2 times 17 times 2 times 17, and 63 is 7 times 9, so that's 3 squared times 7 times 270. 270 is 2 times 135. So first we have a 2 and then 135 something. So in fact, this will give us 2 to the third power times the whole thing, and all of these are odd, right? So everything to be odd, which, let me see. This one is 5 times 27. So this one is 3 cubed times 5. Here we have 3 to the 5th power times 5 times 7 times 17 squared. This is how we do it. And that applied to this analysis, sum of odd divisors. It means all of these divisors are free of 2. Then we will have something like, if you really want to find it, it's like 1 plus 3 to the 1st power plus 3 to the 2nd power, all the way to 3 to the 5th power. And then by distributive law, we have like 1 plus 5, 1 plus 7, something, like 1 plus 17 plus 17 squared, things like that. Quite problematic. However, this is the expression for this big O. And the big sum, we know what is going on. So in fact, the contribution for this one will become all those terms contains 2. Right, so if we consider this distribution with respect to 2 and not 2 free, then we know these actually are those terms with 2, right? 2 to the first term, power, 2 to the 2nd power, 2 to the 3rd power. We have the summation for that times all, or times this whole thing. Then the ratio, O to E, we know it will be some ugly things over this ugly things times, right? It's like 2 plus 2 squared plus 2 cubed, something like that. Let me switch back to my work on that. So it's like 1 to 14, isn't it? 2 plus 4, that's 6, plus 8, we have 14. So this is 1 to 14. Right, so this time we try to treat them all. Right, so this is a big O, this is big O. We don't really care what is going on, in fact. And if you list them all, perhaps this will be really problematic time consuming. And so far, let's see, we have spent like 30 minutes for the first 12, and perhaps we can talk about something more for the rest problems. Problem 13. We have this positive integer in base n. So what does it really mean in base n? It looks like still we are talking about base conversion. Let me see, we do have 1 and 10a as well. So this is similar to this 10a, problem 11. So we have that base b. If you remember, this is 2021 base b minus 221 base b. So it looks like this year we have some similarities. However, in the future problems in like last 10, we have a lot of differences. Here we have a lot of probabilities and counting. However, in 10a, we have a lot of geometry for this one. 3 to d base n equal to 263. So that means 3n squared plus 2n plus d is equal to 263. And technically, if this is defined restrictively, then we want d to be in between n and 0. Well, sometimes in the future, you may see that we can define that weirdly. For example, according to some sort of base notation, we may have d in between like negative n to n, or maybe negative half n to half n. It depends on how we define this round up, round down. But still, we're trying to say this one is quite unique, such that we have exactly one expression. All right, so this is the first equation. And what about the second one? And the value for the 3, 2, 4 in base n equals the value for that in base 6. So let's set up another one. So we have 3n squared plus 2n plus 4. And by definition, this is equal to 6 cubed plus 6 squared plus d6 plus 1. Well, looks like the better way is that we can take the difference. What is that? I think it's d minus 4 equal to 10 minus 60. And then we can solve for d, and then we can solve for n. We can get it back. Let me see, what was my answer? I have d equal to 2, and then plug in, we can have the n, and we can find everything. So I believe what I got there was b. Well, please help me check if I got it wrong. Thank you. And next, on this one I like. This one is perhaps the best one I like. So now we have 3 equally spaced parallel lines. That refers to a lot of geometry properties we have. For example, when we have 38, 38, 34, well, if we think of those not coincident, right? Typically in geometry for middle schools, we don't want to consider chords or lines to be coincident. That doesn't mean they cannot be coincident, but if they are coincident, typically we refer those to the same instead of consider they being different. Just like when I introduced the idea for set, typically that is something required for AMC10, 12, and AIME. Typically, we talk about simple sets. We don't talk about multi-sets. It's almost the same thing, like we don't count. However, still that refers to the difference in between like solutions or roots with respect to equations and polynomials. For roots, we count the multiplicity. We want to know how many times it shows up. However, when we talk about solutions, typically we don't count it. But that refers to some problems, like when we do factorization, do we need to consider the power? We do. Well, back to this. Once we have 38 and 38, what does it really mean? That means we have those two symmetric with respect to the center. So if we have the center, here is the center. We want those two chords to be symmetric with respect to each other. And hence, if we drop the height, this is perpendicular bisector, then we know exactly this is 19. And since they are equally spaced, that means if I refer to another chord, perhaps on the bottom here, then this one is defined to be 34. Since by symmetry we know this is half and half, how about we call this to be x? So if I call this x, this is x, then the distance in between is 2x. And now by Pythagorean theorem, then we have some sort of structures. For example, here. And this is r, they are the same. And by symmetry, we know this is 17. So it's like 17 squared plus 3x quantity squared is equal to 19 squared plus x squared. And there we can solve for x. Let me see, originally what was my answer? I think I got it to be B. There we can solve for x, and then we can get it back, solve for x, and then solve for r. Or if you really want, that is a challenge, find the distance. So it is 2x to be our final answer. To see what is going on. And to solve it, a remainder, this is, well, yeah, this is indeed a quadratic. So once we see quadratic equation, always check solutions, because some of the solutions may not make sense. However, if we only have first order, if we only have linear equations, typically that makes sense because that is the only solution we have. But once we have more than one, we need to double check whether one of them is negative or maybe one of them doesn't make sense. For example, in terms of triangles or in terms of geometry, like this is way too large, that doesn't make sense, which violates triangular inequality, something like that. 15. Well, 15 is so traditional algebra problem. So if we know what is a trig, then we can solve for that nice and simple. The jump is that we have x to the 11th power minus x7 plus x cubed. This one first we can factor out x cubed, and there we have x to the 8th minus 7x to the 4th plus 1. In fact, if you know something more about it, actually we can write it in terms of x to the 7th. So we take out x to the 4th here. And this will give us x 4th minus 7 plus 1 over x to the 4th. Why do I do this? Now it's the show hand. We have x plus 1 over x equal to root of 5. That means if I square it, I have x squared plus 1 over x squared plus 2 is equal to 5. This is typically what we like because we have a cross product term to be a constant, and there we can have that absorbed by the other side, which means x squared plus 1 over x squared is equal to 3, and hence we can do it another time, one more time. So we have x 4th plus 1 over x to the 4th, and plus 2 is equal to 9. So we know x to the 4th plus 1 over x 4th is equal to 7, or say subtracting 7, we have 0. Yep. The answer is B. So I believe if you haven't seen this trick before, perhaps you will spend a lot of time working on that. And in fact, solving x and plugging in will be a disaster. So of course, there is a way to solve for x, and you will end up being a disaster. However, if we call this to be way 1, definitely there's a variant. We have way 1.5. Like if you didn't see this through, there are some other ways we can do, of course. So we have x squared plus 1 equal to root of 5 times x. So there we have x squared minus root of 5x plus 1 equal to 0. And one idea is that it's really complicated for us to raise up to some higher powers. So maybe we can think of like x squared equal to root of 5x minus 1. But still, this is complicated comparing to the first one. But this is something we can do, let's say. And if you want to have like more of a combination, then we can think of, for example, x squared plus 1 over x squared equal to 3. And there we have x fourth. Wait, what is that? Plus 1 equal to 3x squared. So x to the fourth minus is equal to 3x squared minus 1. Again, this one can be used to simplify that because we can factor out x cubed. So a few ways to interpret, a few ways to analyze it, and there might be one that works the best. So far, we have seen the first 15 problems. They look really well. However, some of them are not in the last 10. Let's see number 16. Wait. Uphill. Divisible by 15. So originally this is number theory. Divisible by 15 means divisible by 5 and by 3. So we can do it 1 by 1. And divisible by 5 gives us some hint for the unit digit. Strictly greater than the previous digit means if we have 0, then there is no way we can have such number. So directly we have the unit digit to be 5. So it is like something 5. And all we need to consider, right? So this is the first step. The second step is that how can we manipulate, how can we find this number such that this whole number is divisible by 3? And divisible by 3, we know the sum of the digits is divisible by 3, and hence if we have something in the front, then that one will be, say if we call this to be x, then x plus 5, right? Sum of digits, we can do it partially and then add it towards the end. So this one is divisible by 3, hence it is congruent to 0 modulo 3, or say x is congruent to 1, if I did it right. And what else? In fact, prior to 5, like for this uphill integer, we know like 1, 2, 3, 4. So 3 doesn't change at all. So we can have 3 or not have 3. That means have 3 or not is okay, or not. Will provide us 2 copies, right? So suppose we have something like 1, 2, 4, then including 3 or not including 3 wouldn't change the divisibility by 3. And since we have 5 at the unit digits, we know the whole number is divisible by 15, of course. And then we only need to consider 1, 2, and 4, a combination. Like if we have some part of it. Of course, the first one is 1. So then we know 1, 3, right? 1, 5 is fine, and 1, 3, 5 naturally is fine. What about the rest? Well, we have 4, 45 is fine. So then we have 3, 4, 5. By the way, how can we consider the order? Order doesn't really matter because we know this is uphill. So as long as we have all these numbers, then 3 has only one position, one and only one position, such that we can squeeze it in or take it out. So we can multiply by 2. Then apply the same idea, then we can have like 1, 2, 4, right? 1, 4 couldn't work and 2 doesn't work itself. So we have 1, 2, 4, 5. Hence we have 1, 2, 3, 4, 5. So like in fact, during the test, you don't need to write down the bottom line, and there we have this. So the final answer is C. It is enough for us to split into these 2 steps and see what is going on. So this is more like something with respect to correspondence. Next, well, this one is really similar. Let me see if I have a mark there. Because I remember that is similar to some problem with respect to AMC8. Yes, that one was 2004. This one is really similar to 2004 AMC8. Which problem was that? Problem 18. So we're having this like summation, right? So 5 groups of 2 numbers such that we have 11, 4, 7, 16, 17, and then we want to know like which goes where. And for example, for this 4, we know it has to be 1 plus 3. There's no other combination because all of these numbers are different. And then the second smallest is 7. So we couldn't have 1, 6. We couldn't have 3, 4. Naturally, it is 2 plus 5. No other choices. And there we have 11, 16, and 17. In fact, 17 originally we may guess it is 8 plus 9 or 7 plus 10. Something like that. And then we can work on 16 as well. And for 11, we don't have 1 plus 10, we don't have 2 plus 9, we don't have 3 plus 8, we don't have 5 plus 6, so we only have 4 plus 7. In fact, it's done. It's 8 plus 9 for 17, and 6 plus 10. So I don't know why they put this problem here. It's, AMC 8, problem 18, and AMC 10B, problem 17, they are so similar to each other. This one, I believe the difficulty is sort of weird. But that might be the preparation for the next one, because for problem 18, well, for me, I would prefer that being in the last 5, because this one doesn't work really easy. Well, if you read those explanations on ALPS, we do have some quick solutions. However, those are not perfect explanations, I have to say, because if you roll it one more time and you have some repeating even numbers that you already see before, the probability doesn't change, but that was not counted. Like if we have something like 3 factorial or 6 factorial or something like that, that doesn't work well. However, we do have a theory to cover all of these, which is the transition matrix or say transition matrix. However, this one we do need to consider something with respect to probability theory. So in real tests, if you want to do some quick ways, that's fine. But in general, if we want to know what is that, this is not a good idea. Let me see. I believe in 10A we do have another one quite similar to this one. If I can figure that out, that would be better. Yes, that's problem 23. So for 10A, problem 23, that frog jump, frog hop, whatever, let's call it frog hop. So we have some sort of idea like that. And also, this is quite similar to 2020 10A. I believe that's problem 13 or 12. That one is also a frog hop. So we're trying to have this jump in between so that we can tell what is a probability eventually. So we can set up a system of equations. Here we can think of this. Let me make up a table. Welcome in, welcome in. What was that originally? Well, here is it. Let's see. To better explain that, I need 5 columns and 4 rows. Yeah, there it goes. There it goes. So here is our analysis. Like we want to from 2. All right. So originally we have 3 to be rolled, 3 even, and 2, 1. Right. So we have 3 even numbers, and then after a row, I may have still 3 even numbers or 2 even numbers or 1 even numbers or 0. Oh yeah, I shouldn't consider 3 because that is not something I want, because originally if we have an even number, there's no 3, so it is 2, 1, 0, and odd. And so we have a death once we have an odd number. So directly we have 3 to 2 if we roll one of the 3 even numbers. So that means we have a probability for 1/2, right? So remaining 2 even numbers for sure. And then there's no way that we can directly jump from 3 even numbers to 1 even number. There's nothing, and nothing for 0. So what is the rest of 1/2? It goes to odd. Right, so this is 3/6, and this is 3/6. And next, there is a probability that we have 2 even numbers remaining to 2 even numbers remaining. Why? Because we can rotate that existing even number, isn't it? If we get the existing even number, then we couldn't reduce the number of even numbers to be seen, right? We want at least everyone, right? Every even number shows at least one time. So there is one possibility that we have it. So this is 1/6. And then if we want to reduce, we have two more choices, right? Suppose we have 2 in the first, then we have 4 and 6 at this moment. So we have 2 out of 6, which is 1/3. And again, there's no way that after one row, I can reduce 2 even numbers. I can only get one result, so there is 0 possibility. And now you can see that exactly 1/2, there is a way to death to this odd number, right? That doesn't count. And then we have 1 to 2, that is impossible. However, we need to be super careful. What is 1 to 1? Like already, I only need one more even number. However, after one row, I still need one more even number. That means I can get one of these two existing even numbers. So if I have this probability, then it is 2 out of 6. So again, we have 1/3 here. So these two cells refer to resulting an existing even number. And then, of course, we know there's 1/2 moving to death, moving to odd number before we clear out every even number. And the rest will be exactly 1/6 because there's only one and we need that one. So there is only one that we can win, that we can get to this end, which is 1/6. It is almost done. It's almost done. You see this table, it looks sort of tough, but in fact, we can find it. So what does it really mean? That means we can call those, for example, P3, P2, P1, P0, or P odd to refer to this probability such that we have 3 more even numbers to be rolled, 2 more even numbers to be rolled, and 1 more even number to be rolled, or it is a win. So if we write it backwards, like if we write the first equation, second equation, the third equation in this format, then we have like P1. So of course, there's 1/3 probability that it refers to itself. And also we have 1/6 of P0. And what is P0, by the way? P0 is the win. So we can think of that to be 1. That means we need 0 more even numbers to be rolled before we see an odd number. So here P0 is 1. And the next, P2. P2, if we see this is 1/6 times P2 plus 1/3 P1. And definitely we know the probability for odd that something dropped out. We don't need it. And for P3, P3 is exactly 1/2 of P2. Just that. So we're having these equations, and then we can solve for that step by step. Our goal is to find P3, and it is enough for us to find P2 because P3 is just 1/2 of that. So the first one, P1 is equal to 1/3 P1 plus 1/6. And so all of the rest will be success. And then we can solve for P1 there. Let me see, what is my result? P1 is equal to 1/4. And plugging in, we have P2 equal to 1/6 P2 plus 1/3 times that, which is 1/12. And this tells us P2, let me see, what is my result? It's 1/10, good. And there we have P3, which is 1/2 of that, 1/20. Well, this allows the repitance for these even numbers, and technically we don't skip those. That's the key idea. Like if we skip some of those, that doesn't make sense. But after all, they are providing us the same answer. So if you like, you can follow those quick solutions at the very beginning. But again, I would like to introduce this. Once we are doing all these practices, once we are trying to do this analysis, we would like all of these to be in this rigorous analysis so that they are good, they're in this good condition. Next. Number 19. Greatest, least, and we want to talk about the mean. So here are my notations. First, suppose there are n numbers, like if we say the cardinality for that finite set. So we call this to be n. And then we can think of like m to be the max, small m to be the minimum, and then we have some sort of summation, right? So let's use capital sigma. No, that's p. Sum of all these. So this is a sum. And there we can list all these equations and play with this. For example, the first one, if the greatest integer is removed from S, that means P minus the max, then the average, right? So this is n minus 1 is 32. This is the first step. And if the second one, if the least integer is also removed, that means we have n minus 2 to be considered for this one, then the average will become 35. So this is P minus capital M minus little m. If the greatest integer is then returned to the set, so we will have P minus little m over n minus 1. Then the average rises to 40. And also we have the difference, right? The original set, the largest, the greatest, versus the smallest. We have 72. So that gives us m minus m. That is equal to 72. So it looks like the last equation is the easiest one to handle. And can we compare that with respect to some other things? For example, if we subtract 1 from 3, right, 3 minus 1, there we have 8 equal to, well, p and p cancel. So we have capital M minus little m over n minus 1. And this one is provided. So this is 72 over 9, of course. So we know 9 is equal to n minus 1. So n is equal to 10. And then we can recover capital M, we can recover capital P in this sense. So for example, plugging in, what did I do? I tried number 3, so P minus little m, right? So this is 9 times 40, we have 360, and plug into the second one, because if we use the first and third, we have used that, so one of the equations should be not useful, should be useless, and this one gives us 280. And again, if we take the difference, we will have capital M equal to 80. And there we have little m to be 8, and then we can find the capital P, the average, and then we can find the average, of course. Oh, sorry, almost forgot this. It's the 36.8. So again, this one refers to all of these algebra idea. Oh, you may say, when we consider means, doesn't really mean combinatorics versus counting and probability. This is where we use in the United States. I should say maybe not, because you see the relation here is more about algebra. So sometimes AMC10, 12, and AIME, we see when you do your daily practice, when you do your weekly practice, you will see that up to a point that it's very hard for us to proceed, for us to move forward. The main reason is that we need a higher level to interpret what is going on. So we want to combine everything together. Still, if I'm not spending too much time on all of these problems, still I will feel frustrated for some of those, to be honest. So we need to practice, and then up to some point you will see, hey, there is an upper level. Let's move there and see back, right? If you see it from top to bottom, you will see, aha, some of these are connected to each other. And that is something very hard for us teachers to help students to generate. This is something you can obtain from your practice. That's why we say you need to recover lecture notes, you need to do something for your practices, and eventually we'll see, oh yeah, this is my understanding instead of my teachers. Problem 20. 11 segments, all of these are of equal length, and we have this area. Well, this is super hard for me to draw this. I plotted by myself. Why? Because it's very hard for me to find all these angles, and you don't need to. You don't need to. The thing is, how can we represent this area? That is my question. We know all of these are of length 2. So that means if, for example, let me see what is my label. We're having these to be equilateral triangles, one of them to be X, one of them to be Y. So we have 4 equilateral triangles. We have ABX, we have BCX, we have AEY, we have DEY. I don't want to label those. You can see that through your eyes. And then if we have those equilateral triangles, then we have 60, 60, 60, and then together we have 120. Now I want to label those. We have 120 degrees, and we have 60, we have 60, we have 120. So all of these we want to know, right? Those are the key information. And what else? Well, if we have 60, 60, 120, that means if I connect AC, if I connect AD, then something will show up. Let me show you the structure. First of all, we know triangle ABC is easy to handle, and we know triangle ADE is easy to handle. So it is like 30, 30, 120. Because by symmetry, we know ABCX, right? AC is the axis of symmetry, hence we have 30 and 30, 30 and 30. That is angle bisector. And for these, we can find the area. Nice and simple. And then we know the length, right? So this is AC and also AD, so we can use only one of them. What is that, by the way? AC is square root of 3 times AB, which is 2 root of 3. You can either generate the altitude, which is BX, right? Take half of that, and you can see we have 2, 1 root of 3, and double it, we have 2 root of 3. Or if you know trigonometric functions, you can see that directly according to law of cosines or law of sines, whichever is fine. However, one thing I want to mention here is that if you want to move to AIME, we need to know something about like logarithms, exponents, trigonometric functions. For example, for the first 5, 10 questions, we do have something like solving triangles. And if we don't know these, like I can only reach the base level for AMC10, perhaps it's super hard for you to move to AIME because we know it is like either 120 or the top 2.5% of the graders to move to AIME. So we're expecting these good students, if you are, to be eligible, or so you know that already. Good. And then we know this one is exactly AD as well. So once we have this 30, 30, 120 and 30, 30, 120 together combined, we know it's still like 2 copies of that equilateral triangle. We can handle that. Nice and simple. And then for the middle one, we have ACD. And can we solve for that? Of course, yes. We have 2 root of 3, 2 root of 3. So this is isosceles triangle for sure. And we have the base equal to 2, and half of the base is 1. For isosceles triangle, we have angle bisector, perpendicular bisector, or say the median, and also we have the altitude. All 3 line segments coincide, they are the same, so we can solve it by Pythagorean theorem. So 2 root of 3 and 1, then we know the height is root of 11, so then we know the area if inside, and then we have the area multiple triangles, of course. Exactly, thank you. So then eventually we can refer to the area of triangle ABC, the area of triangle ADE, and the area of triangle ACD. And this one we can do it in terms of 1 times root of 11. And there, these two together, you can think of like 2 times this equilateral triangle. And this is root of 3 over 4 times, what is that? 2 squared. So this is 2 squared, and they cancel. So together, the answer is 2 root of 3, which is root of 12 plus root of 11. So add n and n together, we have 23. There we go. So now, as I said, my feeling for 10B is sort of harder, sort of tougher than 10A is that we need some more analysis, and you will see in the upcoming 5 problems. Well, this one is so conventional, so similar to, so familiar to us. We do a lot in China, to be honest. This is quite a traditional geometry practice. Because it refers to all this transformation, like we have this reflection, and sometimes we have the model with respect to translation, and also we have this connection with similarity, similar triangles, as well as Pythagorean theorem. Pythagorean. So once we have these kind of model, we have a lot of such things together. Side length of 1, and we have like 1/3. So this is 1/3. Let me use red. I think red is easier to see. We have 1 together. This is 1, and here we have 1/3, and here we have like 2/3. Well, how can we set up those equations? How can we figure out all the similar triangles? For example, the first one, if we have this to be 90 degrees, then immediately we see this triangle AC prime E is similar to this triangle. Well, we have D to be the right angle, and then C prime, that's sort of far. So how about we call F, DF C prime. So these are the models. These are the powers of models. We typically do that, this kind of analysis. And moreover, if we connect all of these, for example, if we call this G and this to be H, and you will see another pair of similarities as well. We have these. I'll save that for you. You can give it a try. What kind of things do we have, right? The answer is H, and which one is further? We have G and E. So actually, we have all of these kind of things. And moreover, according to this fold, according to this reflection, we know CF and C prime F, these two are equal. So now we have something. For example, we have CF plus CD equal to 1. Say if I set up an equation, say we have CF equal to X. Right, this is X, this is my X. Then the rest will be 1 minus X, which is DF. BF is 1 minus X. And there directly we have this Pythagorean theorem. So see, once I say I have reflection, I have similar triangles, I have Pythagorean theorem, then we can connect all of these together. We have C prime D quantity squared plus DF squared, and that is equal to C prime F squared. I put parentheses just to indicate that prime is just for the point. Then we have something, for example, this is 1/3, which is 1/9 plus DF, this is 1 minus X quantity squared, and that is equal to C prime F, which is CF, so this is equal to X squared. Now then we can solve for X. Don't worry, this is no longer quadratic. Once you see that often, because we have difference of squares, they cancel. Once they cancel, what do we have? In fact, we have this one to be 1/3, 4/9, and 5/9. Again, we have this 3, 4, 5 relation. So this is my C prime, this is D, this is F, this is C. And we are looking for the parameter for A, E, C prime, and now it's done. You see, because we have AC prime equal to 2/3, and consider this similarity, then we can directly apply this relation. That is the long leg, which corresponds to 4, right? We have 3, 4, 5, and the parameter is 3 plus 4 plus 5, which is 12. So actually the parameter for that, the parameter for triangle AEC prime is exactly 3 times that AC prime, which is 2. So in fact, this 21 doesn't look really hard, but actually if we're not very familiar with all these models, perhaps it looks somehow challenging, just like what we have for consider 10A, problem 17, that one with respect to the trapezoid, and we have similar triangles, and I believe that one looked really hard, even harder than this one. Some students told me this one is, well, that one is sort of hard. Okay, so let's quickly move on. Problem 22. Well, this one, well, if I do it in the test, I may give it up. Personally, I don't like it. Personally, I don't like it. This one is not easy. I have to say this one is not easy. And it's almost the same as the last one. The last one is also time consuming as well as 23. So let's skip this and move to some easy ones. How about this? 24. 24 is something about strategy. Well, the reason people put it on towards the very end is that if you haven't seen something like that, perhaps you will feel frustrated. And if you know what is going on, then perhaps it's super easy. First, let's see who can be the winner. The one who removes the last brick wins. And typically, these kind of problems can be super hard because they are really complicated. There's no way for us to generate all these paths. So when we say there's a way that we can move, right? I take a move, you make another move, and then I do the third one and keep going until we know who wins. There are so many ways, so many paths. That's why we need computer science. We need these neural network and a lot of things and approximation. We have these supercomputers to work on all of these. Is that this is very hard for us to analyze. So we want to find some pattern. We want to abstract something that we can handle. For example, one thing that we know is if we can apply some sort of symmetry, then definitely we know if the first player does something, then the second player can just follow, right? As long as there's no possibility that for the first player, he removes everything, then the second player can always take something, right? This kind of symmetry can be a general sense. For example, the most basic ones is like a pack of stones. You can take like every move 1, 2, or 3, then the summation will be 4. So you can think of 1 plus 3. The first player take 1, then the second player takes 3. And if we have the first player takes 2, then the second player takes 2. And if the first player takes 3, then the second player takes 1. Something like that, such that they form a symmetry, and then we can think of like the remainder modulo 4 to see whoever has the winning strategy, something like that. And there we have it. Can we make an operate? Yes, we can make an operate. For example, now we have these 4-2 relation where we want a win for Beth. Right, so if there's any possibility that we can generate, that we can reproduce as a winning strategy, then it's fine, right? At least we know for symmetry, it's okay. For others, really hard for us to recover everything. Well, I couldn't list all of them, to be honest. Well, if we have something like that, then what can we do? Right, so if we have, say, 6, 1, 1, is there a way that we can generate a symmetry? That's our question. Like if we have 6, 1, 1, is there any possibility? The answer is yes. No, not really. If there's a way that the first player could generate by symmetry, like after the first step, we have some sort of symmetry. That means the first player becomes the new second player, right? Once we have a symmetry, then Beth takes something, then Arjun takes something. So there's no way Beth can win. That means there is a winning strategy for Arjun. for example, if we have 6 and we are allowed to take either 1 or 2, right? We're allowed to take 1 or 2 adjacent bricks. That means that 1 and 1, there's no way for us to control. We can think of something with respect to that 6. We can take that 2. And we can take that 2, 2, 1, 1. So we take the middle 2 out. And now, no matter how Bath takes, right? Now Bath becomes the first player and Arjun becomes the second player. So Bath takes something and then Arjun could take something, right? If Bath takes something from here and then Arjun can take something from here. They don't need to take from one pile. But if you have something taken, I have something taken. If you have something taken, I have something taken, right? We can group that by a 2 and 1. So if you take something from that 2, I can take something from my 2. And if you can take something from that 1, I can take something from this 1. And eventually, of course, Arjun has some copy, right? Arjun has a step after Bath so that Arjun could win. Arjun wins. That means after one step, there is a possibility that we can generate a symmetry, then Arjun wins. Right, so if and only if, after one step. Well, we shouldn't say if and only if, at least if there is a possibility, if after one step, there is a symmetry, it's fine. There's a symmetry. And then we can check for the rest. And by the way, the answer is B. So let's argue for C, D, and E, because it's very hard for us to prove B is correct at this moment. Well, what about C? 6, 2, 2. Well, since 2 and 2 are symmetric, so we can, again, play the same trick. So we have 2, 2, right? So the first pile, we take the middle 2 out, and then we have 2, 2. So now one of them belongs to Bath, one of them belongs to Arjun. So Bath goes first, take anything, and then Arjun just copies. So no matter how Bath works, Arjun always has a move, and eventually Arjun could take the last brick for sure. What about D? What about D? Well, 6, 3, 1. Well, if we take a 3 or 1, that means we couldn't generate the symmetry. However, if we can break that 6 into 3 and 1, we're done. So this time we can think of like 3, 2, 1. So we take this 2 out. So there we have 3, 1. Two groups. We have 3, 1, 3, 1. So Bath takes anything, Arjun takes that, follows. And what about 6, 3, 2? Well, these two are the same group. So now we just take 1 in the middle. So we have 3, 2, and there we have 3, 2. By symmetry, Arjun always. That means the only possibility, after all, is B. And definitely we can see that at least after one step, there's no possibility for us to generate this symmetry. However, to prove it still is quite hard, right? 6, 2, 1. We need to do something with respect to that 6. However, there's no way we can obtain a 2, 1 because we need to take 3 bricks, but that is not allowed. So there's no way that we can take 2, 3, 1, right? We take the 3 to get 2, 1, 2, 1 symmetry. This is not allowed. And then no matter how you take, or you can generate all these paths to check. After 2 steps, we can obtain a symmetry, hence Bath could win. So that means Bath wins. This is 24. All right, so the rest of 3 are super hard. Let's do it one by one. Problem 22. This one, what is the final answer? Let me see. That one is 471. Yeah, this takes time to do it. And in fact, this is quite brute force. So if you know what is going on, this is just algebra. But in general, this is problematic. This is a probability. Sorry. This is counting in probability, or in general, we call that combinatorics. How do we assign all of these? We have 5 blocks and we have 5 boxes. And then we want to randomly put those, right? Each box receives 3 blocks of the same color. So 1 for each, right? How do we assign? Well, if we're looking for the probability, then we know it's something like the count of the events that we're looking for over the space, or the total number of events, the total space, we know what is going on, because we have 5 factorial, right? This is for one person, and then the other 2 also have such many. So in fact, the very first question can be easily answered. So we have this 5 factorial cubed, super large. No worries. And then what can we find for at least 1? I believe that is the challenge. Well, if we take the opposite, maybe that's even harder, because sometimes in probability we may think like at least 1, the opposite is none, but still when we consider like none of these are in the same position, are coincident, still we need to consider like 4 colors, and then for the next color, how can we arrange that? And then for the next color, how can we arrange that? Still we have to work on all these details. Not easy. And here the application. One of the ideas is to apply principle of inclusion and exclusion. So we can think of like exactly 1, exactly 2, exactly 3, exactly 4, and then we can manipulate, like include, exclude. We can play with all of these. So first of all, if we want to determine like all of these with the same color, what can we do? Well, first of all, suppose we have exactly k. If we have k coinciding, right, k same. But first of all, we have to find k out from these 5 to determine these boxes. And next, we want to permute, right? We want to assign these. So sometimes we use, say, P51, like people may use like 5P1 or maybe P15 or something, whichever we like, but we can use in general according to factorial. We'll have like 5 factorial over this 5 minus k quantity factorial to determine the color assignments. For all of these, and then the rest, we need something else. What are those? We need to determine which box is it. We have still the rest. We have, let me see what was my notation, because this one, sorry, this is still not very easy to memorize everything. So this is 5 minus k quantity factorial of this whole thing cubed. So for all 3 people, we need to manipulate the rest, because we don't know for those colors. We have no control which one goes where. So we can still play with the rest. That's how we pack it up. And originally we want that with 1, and then we want to consider, we need to take care of the 2 same color, because we double count those, and then we need to subtract it. However, then we lose all those counts with respect to 3 colors, and then we need to add those back. And then for the 4 colors, we need to subtract those, and for 5 colors, we need to take it back. So eventually the probability, well, to explain everything will take too much time. So the final probability will be something like this: 1 over 5 factorial cubed times this whole thing. Let me see, what are these? The first term will be 5 choose 1 times 5 factorial over 4 factorial times 4 factorial quantity cubed minus the second one. So we just follow the pattern. 5 choose 2 times 5 factorial over 3 factorial times 3 factorial quantity cubed. plus 5 choose 3 times 5 factorial over 2 factorial times 2 factorial quantity cubed minus 5 choose 4 times 5 factorial over 1 factorial times 1 factorial cubed. Plus the last one, which we have 5 choose 5 times 5 factorial over 0 factorial times 0 factorial quantity cubed. And the rest will be simplifying everything. So let me shrink that a little. Now I have some space for myself. Well, 5 choose 1, 5 choose 2, 5 choose 3, and all of these kind of things, we have 5 factorial already. So this is 5 factorial over 1 factorial, 4 factorial, and then we have 5 factorial, 4 factorial, and 4 factorial cubed, and something like that. So to simplify this, we have like the square term for 5 factorial. To simplify this, we have 1 over 5 factorial. And there we have this 4 factorial over 1 factorial. Notice we have 4 factorial cubed over 4 factorial squared. So they can. And then the second term, we have 3 factorial on top, and then we have 2 factorial on bottom. Well, this is mainly about algebra. So if you don't follow, just try to simplify this by yourself. You can see what is going on. Because for the pattern, just take a little bit of time and you will see what is going on. We have 2 factorial over 3 factorial here. And then we have minus 1 factorial over 4 factorial and plus 0 factorial over 5 factorial. I hope that is the end. However, this is not very easy to find. This is 24, and then we have 3 factorial of 2 factorial. This is 3, and then the next one is the reciprocal 1/3 minus 1/24 plus 1 over 120. It looks like we want to borrow 120 to cancel all of these. So a better idea is to have 5 factorial squared times the distribution for that. This is 24 times 120. And minus 360 plus 1/3 times 120, which is 40, minus this is 5, and the next one will be 1, and then simplify everything. Still, that takes time. That's why we say this is kind of hard. Brute force, but still not easy. So this is 71 over 400, and the final answer asks for the simplified form, the summation for numerator and denominator. So we need to be super careful to find this. The answer is 471. This is all for 22. And for 23, well, this is really AMC10 genre. So I know a lot of people hate it. I don't like it either, but this probability still we can find what is that. So for example, we want this boundary, right? We want this boundary for the circle with the center of the circle, because we have that inside the outermost boundary. So we know the extreme cases are exactly 1/2, right? So that's the radius out from there. This is the first thing. So we have like 8 minus 2 times 1/2. That's the radius, 1/2, right? Diameter 1, yes, diameter 1. So the radius is 1/2. That means this is 7, and hence a probability is something over something. And this one is 7 squared. This red square, which is 49. And all the rest will be something on top. We want to know, like, when can we have this coin? When can we have this little circle intersecting, or at least tangent to some part of these black regions, these shaded regions? So we can think of that one by one, because by symmetry, we know the 4 corners are the same. So we can only take care of one corner, and then we need to take care of the center. So to take care of the center, what do we have? Of course, if I have a circle here, I can have it touching. So if I have that moving along this side, it's okay. So first of all, we can obtain some sort of square. However, I couldn't rotate it, so let's use this line segments. I have these one, this part, and I have another one. Oops. I have another one here, I have another one here. And I have another one here. Of course, we know these are the boundaries. Of course, inside, if I have this coin, if I have the circle sitting in, definitely there is intersection, so we don't need to worry about it. And what about the rest? The rest is that once we have the little circle here and moving towards the other side, I need to have this point touching. So it is like rotating along these curve so that the center is still just one unit out from that point, out from that vertex, so that we can always have the circle touching tangent to this square, or to be precise, touching this square, because tangent doesn't make sense here. So then we have this curve, right? If we have the center within distance 1 towards the square, definitely that point, that circle will intersect. So we will have this. Let me erase some part of that. Then we will have this part as this sector. It's like 1/4 of the circle with the same radius, because we know this one is exactly 1/2. And then we have these 4 corners. In fact, this center piece is easier to find comparing to those 4 corners, to be honest. So the center piece, so this is step 1. And step 2, we're looking for the top. We're looking for the area, the events on top. Case 1, we're looking for the center piece, and the center piece contains those 4 rectangles, and 1 circle, because we have those 4 quarters together. They combine with a circle, 1 circle. The circle, we know it's of radius 1/2. It's easier to handle, and side length is 2√2. So we have 4 times 2√2 times 1/2. Those are the areas inside. And don't forget, we have this large square inside, which is 2√2 squared. This is equal to 8. And 1/2 squared times pi. So this is pi over 4, and here we have 4√2. So we can count all of them, sum over. And the second one is that we have those 4 corner pieces, 4 corners. Now it becomes really frustrating. Suppose we have this zoomed, right? We have this large piece here. I have some sort of triangles. Well, of course, red lines correspond to red lines. So we're thinking about like some circles here. If I have a circle right as a moment, or better, let me change those to black colors. Cut it. So suppose we now have this black boundary to see what is going on here. We know this is the triangle we're talking about. Let me zoom in. Where is that coin? So originally we have this coin touching from here. So we know those are on the boundaries. However, we don't like that, because to be honest, this has nothing to do with any black part, right? We have the center pieces we don't want to consider, and we have a corner and it's not touching. So we want to shift it down. We really want to shift it down until here. So this is the starting point that we want to talk about. Let's make it a mark. So this is the first point that we want to talk about. And also, given this circle, we want to shift it along this side. So this will give us the boundary. So that will be the red line connecting here. And moreover, what about the other sides? In fact, we have seen that this part is something like within the boundary. We know if I have my circle not on this hypotenuse, but moving inside, definitely it will hit. Well, let's consider this circle moving. right? If I have something here, definitely we will have some sort of intersection together with this black triangle, right? This is the touching case. And once I move inside, it's okay. And if I shift it down somewhere until that existing boundary for the red line, then it's done. So all we need to consider is the measurement of all these. So let's consider one by one. Here we know it is 1/2. This is 1/2. They're good. The thing is, how can we know the side length or the leg for the right triangle? Let's see, we have length 2 for those right triangular regions. So we have these to be 2 and these to be 2. However, we don't have the red lines. We don't have that red right triangle having leg length 2. We don't have that. So we need to check what are those. Let's move this circle back. Towards this extreme case. In fact, we only need to consider what is the difference. You will see that if I can mark this, right, all we need to consider is this difference. How can we make this shift? If we know that, then we know exactly the side length of the right red triangle, and we can find the area. And for that, what is a model? What is a model? We're having this to be tangent. We're also having another tangency. And moreover, let me zoom in to be as much as I can. Then we have a few relations here. Say I have this to be, how about I call some part of these to be A? Well, if I call this, right, this is a tangent point. Let's drop an altitude. Let me make it thinner. So if I call this part to be A, and then this part is A, and then the hypotenuse is root of 2A. And by symmetry, this is tangency of circle and lines. We also have this part to be root of 2A. This is root of 2A. However, we cannot solve for that at this moment, can we? Very hard. But we know that the radius is 1/2. What does it mean? We're having this trapezoid. We're having this sort of trapezoid. Can we solve for that? Perhaps we can. Because we also have this side to be 1/2, and we can show that this one becomes this right triangle. We have the hypotenuse to be 1/2, and here we have on top root of 2A, and on bottom we have A, right? Exactly a rectangle, and here the bottom leg is exactly 1/2 minus A. We have part of that to be A, and on top we have 1/2. So exactly we have 1/2 minus A to be the bottom leg. Now Pythagorean theorem, we can find this A. So we have this 1/2 quantity squared is equal to root of 2 plus 1A times A quantity squared plus 1/2 minus A quantity squared. We can solve for A, but be super careful. That change is root of 2 times A. All right, so that's why 10B for me is sort of harder than what we have before. Let me see, what is that A, by the way? I have found it. I have found it. Trust me. A is equal to root of 2 minus 1 over 2. I did my calculation. And then we have root of 2A equal to something, which is something like root of 2 minus 1 over root of 2. And you can simplify that, of course. And there we can find the area of the corners. So this is like 4 times 1/2 times the square of that. Root of 2 minus 1 over root of 2. Be careful. What are we adding? what are we adding? We know the increment is root of 2a, but then the rest will be 2 minus 1/2, right? The blue part is 2, but we need to remove 1/2. So we have 2 minus 1/2 quantity squared. We need to simplify that. And in the future, eventually we need to add 1, 2, 3, 4, these 4 components together. And that gives us the final answer. And that is the reason it is super hard. So let me show you the final answer for that. This one will become pi over 4. So that comes from the centerpiece. And also we have 6 root of 2 plus 11 plus 6 root of 2. And then we need to simplify that eventually. So this gives us a final answer, which is 1 over 196 times 44 plus 24 root of 2 plus pi. Oh gosh, that is the final one. And then we can check for A and B, and then you can have A plus B, which is 68. Yeah, that's the reason I hate AMC10B for this year. To be honest, I draw the solution. I need to indicate every single piece. It takes me a lot of time to figure out how to have all this details squeezed in. All right, so the final answer for this is 68. And we have 25 to be shown. And this one, by the way, that is also similar to something. 2011, I believe that's 2011. 2011 10B, probably it's problem 24. Couldn't memorize it well, but it should be something like that. Or 10A. Hopefully it's 10B. But what is that? We're trying to raising up these lines. We're trying to play with A plus B. So in fact, first we need to figure out the structure. What is the structure, by the way? We're having all of these lattice points where we have a lot of lattice points. Well, this is not what you should plot, but to indicate what is going on, right? We have this line, and then we have a slight change. Exactly 300 points lie on or below. So that means there's no change. So that means there is no change from the lower bound to the upper bound. There are 300 points. So if we're thinking of this relation, technically the lower bound will be, we have some points exactly on the line so that we just reach 300. And the upper bound will be something like, if we move slightly more, then we'll have 301 points. So ideally, we will have closed interval, closed part for this lower bound and open part for this upper bound. This is what we are expecting for this analysis. And by the way, those are set theory terms, close and open. However, we only consider this value. So if we see something like lower bound small m to capital M, this still the difference is m, capital M minus little m. So we don't consider a point with some length, so it's okay. However, this will be our imagination for the final result. And now we need to figure out what is the upper bound, what is the lower bound. We want to find those two values. Well, at least we have 1 to 30, so it's like 1 to 30, so it's 30 times 30. In general, we have 30 times 30, which is 900 points. And then we want 300 points exactly on that. So we're expecting some sort of a square in the area. We want that to be 1/3. How can we have that? The area. Suppose we have the side length to be 1, then we have exactly 2/3 of the height. So then we will have the area roughly about 1/3. We can use this as an approximation for the number of points, because once the number of points are super large, their really close to each other. So now we can check for this. For example, if we have 2/3 for this loop, how many points are there? Or I wouldn't spend too much time on this, but 2/3 is exactly the lower bound. So if we have some number slightly smaller than this little m, then we no longer have 300 points. However, it will be super tough to find the upper bound, in fact. So I'll spend some time talking about the upper bound. Well, it looks like we need to consider the jump, right? We just say that there's no change for the number of points. So we're expecting some slight change out from these lines. If I have some new points included, like digested, captured by this line rotating upward, then we will have the 301st point there. So we're trying to see which point can be hit at the very beginning once we raise it up. So here we have the slope to be 2/3. And then we can check that for 1, 2, 3, up to 30. In fact, we need to be super careful for each point. The shift, the jump changes not in the scale. It is more like some zigzag relation. For example, for 1, let's do some analysis. For point 1, originally there's nothing, right? Let's call those old and new. Originally there's 0 point beneath that because we have 1 2/3. And if we want to hit the line, or say if we capture one more point from 1, we need that to be 1. And what is the new slope? The new slope will be 1. However, that's too large, right? We need to find the first time that any such integer value will capture a lattice point there. And then for 2, originally we have 1 point because we have 2 times 2/3, right? So this is 4/3 for that y coordinate. So we have already captured 1. And if we want to capture a new point, we will have 2 points or beneath that or on that. And the slope for this will be, again, 1. This is 2/2. Well, you may call these to be the same. However, it is not. Well, for 3, we have 2 already, right? That is on the point. 2, 3, 3, 2. And then the new one will be 3. Still, you think the slope, hey, it's 1, isn't it? Not really. We'll change that now. For 4, things will change. There are 2 points, right? There's no 3 point. Do we have? No, we don't. We have 8/3, so it's slightly smaller than 3. And then if we capture another point, we'll have 3, right? So 4, 3, we'll touch that. And then the slope will be 3/4. You will see it's dropping. That means the line couldn't touch slope 1. We couldn't capture that 1, 1, 2, 2, 3, 3. But then we can keep moving. And for 5, we have something like 10/3. Actually, we can capture 3 points. There are already 3 points below or on that line. And if we want to make this the change, it will capture 4, right? 4 points on the line or below the line, which tells us the slope is 4/5. While comparing to 3/4, this is larger, so we don't want that. And you see the slopes are no longer the same. And for 6, we have already 4 points and we want to make a change. For 5, you will see this is 5/6, which we don't like as well. And now, along the analysis, you will see the next one will also capture 4 points already. And then if we want to hit that, the next point, we will have 5. And then there we will have a new slope to be 5/7. And then you will see that for 8 and 9, those two are definitely not accepted because they are larger than 5/7. So it looks like we're checking for this 1. So this is for 1, the slopes. And then we have, this is the x coordinate. We have slope 1/3 for 4. And the next one is 5/7, 5/7 for 7. And we know those are the lower bounds. Those are the smaller numbers. And you can see the pattern there. And before 30, we have, let me see, eventually we have 28 there. So up to the very last point, we have 28, but we need to be careful what is on top, right? So on top, in fact, is 135 instead of 147. Also an arithmetic progression. And what is that, by the way? So on top, we have, say, suppose we have n here for the x coordinate, and then we have like 3 and, oh, we have n there. See. Let's do this. Suppose we have 3k minus 2, right? So this is the kth. Then on top, we have 2k minus 1. So the last one is the 10th one. We have 3 times 10 minus 2. Then on top, we have 2 times 10 minus 1, which is 19. And in fact, we see all of these are dropping. So in fact, the upper bound for this slope is 19/28. This is how we find it. Eventually, we know this. Capital M is equal to 19/28. And little m is equal to 2/3. And so this is the interval from 2/3 to 19/28. And there we can find the difference, simplify it in terms of a over b, which they are relatively prime, and then we can find this on the sum. The sum is 85, by the way. Oops, I have taken that space. Let me move that a little. Good. So there we have the final answer to be 85. That's the reason I say this 10B looked sort of harder, because for 10A, in fact, I went slower than this, although that takes longer, but we went through that one by one, really careful. Well, this is for 10B, and well, I have problem 26, and this is not 10B. So quick intro about AIME, and some of you may have heard about it. So some infos, we have 3 hours, we have 15 problems, and all of these are 3-digit integer. So ranging from 000 to 999. So in fact, you can think of that as 1 out of 1,000 multiple choice if you really like, but let's consider that to be short answers. What does it mean? That means if you can do all of the questions, you have 12 minutes per problem. However, technically, for most of us, there's no possibility for to do that. So you can set up your goals. For example, 6 problems, 8, maybe you can think of like 7, 5 or something, and then say 10. Typically, it's enough for us to consider 10 or 12. Then you can find the average, right? 30 minutes per question. For 10, we have 18 minutes, and then we have 15 minutes. There you can see how long you can expect to spend, or say waste, on every single problem. Right? Once we have around like 20 minutes or so, right, in between 6 to 10 problems, 20 minutes or so, we have relatively relaxing time to do whatever we like. However, according to these analysis with respect to AMC10A and 10B, we notice that actually we need a lot of calculation and analysis. So that requires more calculation and advanced, or say higher level. So you need some tougher, or say harder calculations. And also we need some more models with respect to geometry, with respect to number theory. However, typically for number theory, it's okay. In middle school, in secondary school, there's not too many things to cover. So if you know what required for AMC10, probably it is enough for AIME However, for probability, something like what we have for that 23, yeah, that one with respect to the boxes and blocks, that we need a lot of counting. For example, you need very complicated principle of inclusion and exclusion, or maybe a very complicated caseworks. You need to spend a lot of time. You need to be super careful with respect to all of these. And for geometry, now we need, say, tricks. And for calculation for algebra, we have complex numbers, we have logarithms, we have exponents. So once I heard students asking why we need to learn trigonometrics for AMC10, that means still we don't have a whole structure of what is going on for secondary school mathematics, although that is a very good start, a try for us to get familiar with AMC10. In fact, we do need trigonometric functions, we do need logarithms, we do need exponents and complex numbers to help us figure out what is the general structure. And all of our practices and analysis, we shouldn't stop here. Like if you're running for 100 meters, for your practice, you may run like 150, 200, or maybe 1,000 to save your energy, such that once you only contribute to 100, you can take whatever you like. And it is the same thing that once we prepare for AMC10, we may touch some of these AIME problems. And once we want to prepare for the first 10, 12 AIME problems, we need to touch like the last 5 AIME problems. So we need to have first a general view and then split all of these in details, write every single step along the analysis, like daily practice. And once in the test, you don't need to write down everything. You will feel, wow, time flies really slow. Well, that's so far what I want to share with you. If you have questions, just post it while we're sort of exceeding the time. So some short questions and answers I will share. And if we have some harder questions, maybe we can talk afterwards. Let me see. Yeah, originally. What is PIE? PIE stands for Principle of Inclusion and Exclusion. PIE, Principle of Inclusion and Exclusion. So we need to count step by step, part by part, and if there's overlapping, for example, it is not very easy for us to split in very good characterization of caseworks. Then maybe after we apply casework, then we need to take care of the overlapping, like how many times it was overcounted, then we drop it. Or if we miss some part, then we need to add it back. Things like that. How to develop transition matrix? Well, that will take a lot of time to talk about. So I'll just introduce how to study for that. Transition matrix is part of probability theory, and moreover, this one in the more specific category is something about stochastic process, or stochastic analysis. It's more like a college level or graduate level course for probability. However, we apply the very basic level theory for this, so we can check with respect to probability. It's like for finite. or countable cases, how we can move from 1 to 1. We list this table. So you can refer to this, you can refer to probability theory. And this is super super helpful with an AMC 10 and 12. Because it is not very easy for us to develop some of these infinite jumps, but then we know what happens in between one state towards the other, so that we can set those up for like the stable status. That is the theory. Anyone else? All right. If that's good, then we'll call it an end for today. How does it sound? Well, we will post it on YouTube. Yeah, YouTube. I believe it's YouTube. So no worries. You can revisit us again and again and again. Hope my share helps you with your math learning with AMC10A, AMC10B, as well as AIME. All right, that's all for today. Thank you.